Okay, finally we come to question 4. I think this is the question that gave most of the students a lot of problems. Actually, you can't actually go in and immediately try and solve the question. So what you need to analyze is actually the process it goes through. So what the jeweler wants is it wants to mix about 5% of silver and obtain a 95% gold. Okay, so we need to set up the system. So what we can do is we let M be the mass of the substance that's obtained right at the end. So using that, then what we can see is that 95%, okay, would actually be gold. So that would be 0.95 M. And then what we will also have is 5% would be silver. So a common error that a lot of students did here was they let M be the mass of gold and then 0.05 M to be the mass of silver, but that would not make up 5% silver. Okay, and it would actually be less than 5% silver. So we have set up the system. Of course, some students have actually let the final substance be 1 kg, but I would prefer that by now you should be able and comfortable enough to be able to work in terms of arbitrary mass. Okay, we are told that the jeweler actually melts some pure gold, so we can assume that the gold was already initially in a liquid phase, and then he adds the correct weight of silver. And the initial temperature of silver is 27 degrees Celsius, and if you compare with this melting point of 1240 Kelvin, you do note that the silver starts off in solid form. So what the jeweler simply needs to do is add the solid silver into the gold, and logically the gold should be hot enough to melt the silver so that he can mix it together. There is no need to actually account for the solidification of the final substance, because logically after you mix it together you just let it cool down. But what we want to note here is that the final mixture should be at the melting point of gold. And when it is at the melting point of gold, the silver should logically stay still as in a liquid phase, because its melting point is actually lower than that of gold. So since we have two substances, we can further break the analysis up, and it's actually easier to analyze if we look at gold and silver individually. So we know that the gold starts off in liquid, and this is the initial temperature that we actually want to determine. So this is our point of interest. And we know that for the gold, eventual temperature is going to be 1340 Kelvin. And so it should still stay as liquid, because we're going to just let it solidify on its own. And for the silver, it actually undergoes quite a few changes. So for the first change, it actually starts off as a solid at 27 degrees Celsius. Now, since we have both two types of units here, I'm going to convert my degrees Celsius into Kelvin. And because this is only in whole number, there's no need to add the 0.15, okay, because all the values are actually at most 3 SF. So let's keep it at 3 SF, and this is 300 Kelvin. Okay, so it has to first undergo a temperature change before it can actually melt. So it needs to move up to 1240 Kelvin. Then from solid, it undergoes melting to liquid, and in the process, it stays at 1240 Kelvin, and finally we want its temperature to be 1340 Kelvin. And what we can see here is the gold is going to lose heat, and this is going to gain heat in the process. We can also further put in, so we see for here it's just going to be a temperature change. This part as well is going to be just a temperature change. This is going to be a phase change, and this is going to be a temperature change. And assuming that these are the only two interactions that are taking place, the two substances only exchanging heat, then what we can say is that the heat gain by silver is going to be the heat lost by the gold. And let's start off with heat loss by the gold because it's easier. So the heat loss by the gold would be 0.95, the mass, multiplied by the specific heat capacity of the gold, which we can obtain from the table. And we see that regardless whether it's in solid or liquid, so here we are actually considering a liquid is 1200, just double check the units, joules per kg per Kelvin. So it's 129, okay, joules per kg per Kelvin. And the temperature, its initial temperature is actually higher than its final temperature. So this is one side of our equation. The other side of the equation is a bit longer. It first undergoes the first stage, temperature change, so that would be 0.05 M. The specific heat capacity of silver, seen from the table, is 235. So that's 235. And the temperature change is from 1240, and that subtracts 300. So that's for the first stage. In the second stage, it undergoes melting. So it's 0.05 M times L. So the specific latent heat of fusion is 105. But again, always be suspicious. Double check your units, and it's in kilojoules per kg. So it's actually 105 converted to SI unit. Kilo means times 10 to the power of 3. And finally, we have our last stage where it undergoes another temperature change. So that's 0.05 M times 235, and which is 1340 minus 1240. Now I do notice in a lot of presentation, some of you actually do a lot of simplification before putting in the formulas, plugging it into the equation, but it makes it difficult for the examiner to mark because then we have to tally where the numbers come from. It would be good if you can actually directly transfer the number, at least in the first step, so we know that where the numbers go. It would be even better if you can express everything in terms of symbol first. So before we continue our simplification, you always look for common terms, and here M is common, you can actually factor that out. And from here, you can actually solve for your TI. So after some algebraic manipulation, so let me just give you an intermediate step so you have something to check for. And I think what you will have is finally TI is equals to 1480 Kelvin. So that's the final answer which you can actually check for.